Great. Hello and welcome everybody to the International Physics Symposium. I'm very honored to introduce you today to our opening speaker. Dr. Halpern is a theoretical physicist who applies creative techniques across diverse areas of science such as atomic, molecular and optical physics, condensed matter, chemistry, and high-energy physics to gain new perspectives. As we will learn, Dr. Junger likes to refer to her own research as quantum steampunk, after the artistic and literary movement of fictional steampunk. Just as this movement unites Victorian style with sci-fi tech, quantum steampunk attempts to update thermodynamics for modern quantum systems. In particular, we will be learning today how Dr. Junger applies techniques from quantum information theory and thermodynamics as her main weapons to attack problems across these many areas of science. To mention some of her achievements, Dr. Junger graduated from Dartmouth College as a co-valedictorian, received her PhD at Caltech under John Prescoll's supervision, and her thesis won the International Ilya Prigogine Prize for a thermodynamics presentation. Beginning in fall 2021, she will also become a NIST physicist, joint Quantum Institute affiliate, and joint Center for Quantum Information and Computer Science Fellow. We are now ready to start.
Thank you very much for the introduction, as well as for the invitation to be with you. Thanks everybody for tuning in. I very much apologize about the late timing. This is something that could happen only in the pandemic. I checked the time multiple times, but thought that the time was in a different time zone. So I apologize about that. And I look forward to talking with you. I'm glad we could be together regardless. So I am very fond of probability distributions. How come? They describe quite a lot of things in our world. For example, I live in the Boston area, and the weather in the Boston area is a very, very random variable, as you can see from the icons at the bottom. We can model the dominant weather on any given day as a random variable x that assumes one of many possible values. So if the dominant weather is rain, then we can associate that with a value x1. If the dominant weather is sunny, we can associate that with a value x2, and so on. Then if we watch the weather for many, many days, we can infer a probability distribution, the probability that on any given day, the weather will be rainy or sunny, and so on. Another example comes to us from classical statistical mechanics. We will often have in mind some big system like a classical gas in the box that has Avogadro's number of particles. This number is much, much too big for us to be able to track all the particles, know their positions and momenta at any given time. So instead of trying to do that, we label all the possible microstates, all the possible configurations of the particles, and we ascribe probability densities to the microstates. So we ask, what is the probability density that's at any given time? Particle 1 is in position x11, particle 2 is in position x12, and so on, and that these are the momentum values. We have this probability density for each of the possible microstates. Then we associate each one of those arguments, the position of particle particle 1, the position of particle 2, and so on, with an axis in phase space. Here I've depicted only 3 axes because we can see in only 3 dimensions, but there should really be more. And we think of the probability density as some blob in phase space. So we can represent a classical statistical mechanical state with a probability distribution. We might wonder, can we represent a quantum state similarly with a probability distribution? By a quantum state, I mean a density operator, or technically a trace 1 positive semi-definite linear operator. By trace 1, we mean just that if you measure the state, then you will obtain some outcome. And by positive semi-definite, we mean you can think of this operator as a matrix relative to your favorite basis. If you calculate the eigenvalues of the matrix, you'll find that they're all real and at least 0. By represent a quantum state, I mean write down some function that represents the states, I'll call it p tilde, that has some arguments from which we can calculate expectation values and probabilities. So can we represent a quantum state with a probability distribution? The answer is almost. To figure out how that can be, let's review the axioms of probability theory. I'll talk about a probability distribution that's discrete. It has some number d of elements. This is for simplicity and for relevance for what we're going to talk about later. All of the probabilities are real. They're at least 0, and they sum to 1. Furthermore, they compose in certain ways. So suppose we ask, what's the probability that our random variable x has one of these values, xj1, xj2, and so on? That total probability is the sum of the individual probabilities. Suppose that we relax some of these axioms. Relaxing different axioms and making other parameterization choices leads to different quasi-probability representations of a quantum state. I'll sometimes represent a quasi-probability with this p tilde. It represents the state rho, and it has some arguments analogous to the positions and the momenta of the particles in a classical statistical mechanical system. All quasi-probabilities have the property that if you marginalize over all of these arguments except for one of them, then you get a legitimate probability. So let's take this quasi-probability and sum over all the arguments except for the jth. We get the probability that if we prepared rho and we make some measurements, we will get the jth possible outcome. Quasi-probabilities are perhaps best known as being used in quantum optics, but they've also played important roles in the foundations of quantum theory, in quantum computation, and in quantum thermodynamics. Here are some example quasi-probability distributions which different people might have heard of. One is the Glauber-Sudarshan P distribution, one is the Husimi-Q function. Different ones are useful in different contexts. The most famous quasi-probability distribution is the Wigner function. It famously can go below 0. For instance, here's a representation of the Wigner function for a superposition of coherent states. This blue part at the bottom here represents negative quasi-probability values. The Wigner function is useful sometimes if we're thinking about continuous variable systems like the electromagnetic field, but it's less straightforward in the case of discrete systems, especially sets of qubits, which are the basic units of quantum information and are so useful to talk about when we deal with quantum computing. The Wigner function has this little brother quasi-probability distribution that almost nobody has ever heard of, called the Kirkwood Dirac distribution, which is my favorite quasi-probability distribution in the world. Kirkwood discovered this quasi-probability distribution in 1933, and Dirac defined it independently in 1945. Then quantum mechanics forgot about it for many decades. It's straightforwardly defined not just for continuous systems, but also for all sorts of discrete systems. It has some interesting mathematical properties that I'll talk about later, and it's recently found to be useful in many fields of quantum physics. Here's where I'd like to go in the rest of this talk. First, I'll motivate the definition for the Kirkwood-Dirac quasi-probability and present the definition. Then I'll talk about some of the properties that it has that I particularly like. And then I'll show one way in which it's recently been shown to be useful in quantum physics. I'll apply it to quantum metrology, the study of how well we can measure things. Then I'll step back and have a very, very brief survey of a few of the other applications that this quasi-probability has recently been discovered to have across quantum physics. And then I'll talk about opportunities for future work. Suppose that we perform the following protocol. We have some quantum system, and we prepare it in an initial state I at time 0. This system has some observable big F, which has eigenvalues little f. There's this eigenvalue decomposition. At a time t double prime, we measure this observable f, and we get some outcome little f. Suppose that the system has some other observable, big A, that has this eigendecomposition, and we want to know, given that we prepared the initial state I, and we got the final outcome little f, what is the value most reasonably attributable to A at some intermediate time t prime? We sort of need to take the information about little I and propagate it forward in time, and take the information about little f and propagate it backward in time, and make something like an expectation value that isn't exactly an expectation value. By the way, from now on, for the sake of simplicity of notation, I'll absorb this u into the I. So in the future, when I write I really mean u times I, and the analogous statement goes for f. We can construct a best guess of the value most reasonably attributable in the past to the observable A. It should be some combination of the eigenvalues of the operator A. And we might guess that it makes sense to weight the eigenvalue little a with the probability, some conditional probability that if we prepare little I and we obtain the outcome little f from our measurement, then little a was the value most reasonably attributable to big A. In fact, it's better to put a conditional quasi-probability here. And we can also construct via physical reasoning what that conditional quasi-probability should look like. Again, we are preparing little I. We're wondering what's the probability or conditional quasi-probability that little a is the value most reasonably attributable to big A in between. And our final measurement yielded the outcome little f. We might want to normalize or divide by this inner product in the spirit of Bayes' theorem. Bayes' theorem is within information theory. Suppose that we ascribe some probability to an event, and then we get some new information. We should update our probability so that it now reflects our new information. We do that by performing a division similar to this one. Also, A is an observable. It's a Hermitian operator. Its eigenvalues are all real. So the value most reasonably attributable to A should be real as well. So we should put this whole thing in a real function. We are free to multiply by 1. So we can multiply the top and bottom by this inner product. Now, the denominator is truly a probability. It's the probability that if we prepared little I and we measured big F, the outcome would be little f. This probability is real, so we can move this real function into the numerator. The numerator is yet another quasi-probability, which has an even worse name. It's the Terlecki-Margenau-Hill quasi-probability. And its complex generalization is the Kirkwood Dirac quasi-probability. Let me rewrite that. To concretize the setup, we're thinking about some Hilbert space that has two bases, at least. One is labeled by the A's, one is labeled by the F's. And our quasi-probability, our Kirkwood Dirac quasi-probability, is defined in this way. This is the same expression that we saw on the last slide. We can rewrite it as a trace because the trace is cyclical. So we can move this I to the right-hand side, so it's over here. This I is a pure state. I assumed that at the beginning of the protocol, we prepared a pure state. But if we want, we can prepare a mixed state. So let's generalize this I to an arbitrary state rho. That could be some convex combination of pure states. This is a more general expression for the Kirkwood Dirac quasi-probability. It has a trace with two projectors and a quantum state. So these are some of my favorite properties that make the Kirkwood Dirac quasi-probability my favorite quasi-probability distribution. First, like the Wigner function, the Kirkwood Dirac quasi-probability can go negative. If you want to see an example, then you can check out this paper with, there is an appendix with a particular example with a negative value. It won't behoove us to go through the example here, but here is the example in case you're curious. Also, the quasi-probability can contain non-real values. The Wigner function is restricted to be real, so the Kirkwood Dirac quasi-probability contains an extra degree of freedom. I will go through an example in this case because it's a little bit more exotic, although the setup required is pretty simple. Suppose that we just have one qubit, one quantum two-level system, which you could think of as a spin, the spin of an electron, an s equals 1/2 spin. These are the Pauli Z and Pauli X matrices, which represent the Z and X components of the spin. So suppose that these eigenbases are the A and F eigenbases. And let's choose for our state to be some eigenstate of the Y component of the spin. Then the quasi-probability has this form. So along the top, I've arrayed the possible A states. Along the side, I've arrayed the possible F states. And all of these quasi-probabilities are non-real. The imaginary part of the Kirkwood Dirac quasi-probability is related to the physics of how, if we have a quantum system and we measure one observable, we can disturb another observable. We call these negative and non-real values non-classical values of the quasi-probability distribution because they're inaccessible to classical probability distributions over classical phase space in classical statistical mechanics. As we've already seen, this Kirkwood Dirac quasi-probability obeys a version of Bayes' theorem, which appeals to some of us who are fans of information theory. Also, this distribution can be measured in experiments with weak measurements, which don't disturb the quantum system very much. These weak measurements have been used to measure this quasi-probability in order to perform a new sort of quantum state tomography, which we use if we've prepared some quantum system. We've done it according to, as best we can, according to a fixed protocol, but our engineering is imperfect. So we're not sure exactly which state we've prepared. And we have to figure out exactly what it is. Finally, suppose that the observables we talked about earlier, F and A, commute. They'll share an eigenbasis. Suppose that we choose for our F basis and our A basis to be the same shared basis. Then our quasi-probability becomes an ordinary classical probability. So here's our quasi-probability. If we choose for the A basis to equal the F basis, then this inner product turns into a delta function, and we get a probability. The probability that's, if we prepared the state rho and we measured the observable A, the outcome would be little a. Now that we've gotten to know the Kirkwood Dirac quasi-probability a little, let's see how it can be useful in the context of quantum metrology if we want to measure a parameter as best we can. Here is not an atypical setup in quantum metrology. Suppose that we're building a quantum computer and we create some device that's intended to implement some quantum logic gate, U of theta. At least we try to make this device implement U of theta. Again, we are not ideal, perfect engineers. The device that we create will not behave completely perfectly, though it'll implement some U of theta, wherein theta might be a little bit off from what we want for the value to be. Let's set the origin of our real number line such that the expected value of theta coincides with 0. We have complete freedom to do that. Also, I'll assume that this U is a unitary operator that acts as this exponential. Here, A is a Hermitian operator that generates the unitary. We need to estimate the value of theta. We can do that with the following experiment. We'll prepare some quantum state rho. We'll send it into our device. The parameter theta will be imprinted on the state. Then we'll perform some measurements. We'll get some outcome, let's call it little b, that's distributed according to a probability distribution that depends on the desired parameter theta. And from the outcome and the probability distribution, we learn information about theta. How should we quantify the information that we learn about the parameter? The typical way to do this is to use a quantity called the Fischer information, represented by I. Loosely speaking, the Fischer information is the average amount of information that we gain about theta per trial of our experiment. Here's how I like to think of the definition, or a motivation for the definition. It might not be the best way to think of the definition, but this is how I understand it. Suppose that our measurement yields the outcome B. Then how many bits of information do we gain? The bit is the basic unit of information. The quantification of the amount of information is called the surprisal, and it has this mathematical form. The idea is illustrated with the following example. Suppose that the outcome is completely known. There's only one probability that equals 1, so that we are completely certain before we perform the experiment, the outcome will be little b. Then we learn no information from the outcome because we were able to predict it perfectly. So we should receive 0 units of information. Indeed, if we substitute p equals 1 into this log here, the log turns to 0. So this surprisal quantifies how surprised we are to see the outcome little b, which quantifies the amount of information we gain from the outcome little b. We'd like to know how sensitive this amount of information we obtain from the outcome is to changes in theta. Suppose that this probability distribution didn't depend on theta at all. Then if we found out the form of the probability distribution by running lots and lots of trials and aggregating our statistics, then the probability distribution wouldn't depend on whether theta is 0 or 0.5. So we could gain no information about theta from this probability distribution. The sensitivity of the surprisal to changes in theta is given by the derivative of the surprisal with respect to theta. We're not interested in only one particular possible outcome of our experiments. It would be more useful to know the average surprisal, averaged over all possible outcomes of our measurement. So here we take our surprisal change and we average it. However, you can show that this quantity equals 0, so it's not really very helpful. But we can form a very, very similar quantity just by inserting a square. So this is how we'll define the Fischer information, which is the amount of information we get about the parameter theta on average per trial. Actually, there's a quantity beyond the Fischer information that's even more useful. We obtain the outcome little b by performing some measurements. I've never specified which measurement we should perform. We have lots of choices, but we would like to do our best in learning about theta. So let's imagine that we can choose the best possible measurement that will give us the most information about theta. A measurement in quantum theory is represented by what's called a positive operator valued measure. It's a set of operators, m, labeled by the outcomes of the measurements, little b. All of these operators are positive and they sum to 1. This ensures that the probabilities of the possible outcomes are normalized to 1. A very common example is a set of projectors. This is a representation of the measurement that we learn most frequently in our quantum mechanics classes. But there are generalizations apart from sets of projectors. Now we should express our probability of a possible outcome, little b prime, in terms of not only just theta, but also which measurement we choose to perform. But let me rewrite the Fischer information right here so that each probability depends on our choice of measurement, and let's optimize over the measurements. That gives us the quantum Fischer information, which is the quantity we're going to focus on. Let me introduce a couple of assumptions. First, I'll assume that the quantum state that we send into our experiment is pure. The reason is we want information. We want to learn the value of theta. And if rho is not pure, then our system has entangled with some other system. Our system has leaked quantum information to another system. We want all the information we can get. So we don't want to use a system that's already leaking some information. So I'll assume that rho is pure. It's an outer product of a state psi. And I will denote by rho theta, psi theta, the state that results from imprinting the desirable parameter theta on our state. There is a formula for the quantum Fischer information of pure states. This is the formula. Its form isn't actually important to us. I just want to show you that the formula exists. Also, I'll assume that A, the Hermitian operator that generates the rotation, isn't completely degenerate. So it has at least 2 eigenvalues that differ from each other. The reason is on the next slide. We might be interested in learning how large the quantum Fischer information can become. Let's reason our way to an answer in the following way. Suppose that first, when we perform our experiments, we try sending in an eigenstate of the generator A. This U, the gates, our quantum logic gate in our example, will imprint the parameter on the state only in a global phase. So U acts on the state A in this way. This is the definition of U. And the big A turns into a little a. So this is a global phase. We can't detect global phases directly according to quantum theory, but we can detect relative phases. So we would like to change this global phase into a relative phase and in some sense make the relative phase as big as possible so we can detect it easily. Let's instead try to send in a superposition. Let's send in a superposition of an eigenstate associated with the greatest eigenvalue of the operator A and an eigenstate associated with the least eigenvalue. This transforms under our transformation U into this state. So here's one phase, here's another phase. Let's take this phase and pull it out front. And here we have a relative phase. And what's more, this difference is as big as it could possibly be. It's the greatest eigenvalue of A minus the least eigenvalue A. That's the biggest possible gap. So in some sense, the phase is as big as possible. This is why we assumed that our observable A has at least two different eigenvalues. We can calculate the quantum Fischer information of this state and find that it's 4 times the square of this difference between the eigenvalues. That is the variance of our observable A in this input state. So this is an important inequality. So if we're just using the ordinary protocol that I just outlined for performing metrology, then the most information that we can possibly learn about the parameter theta on average from a trial is the variance. But we can do better than that. Let's add another step to our protocol. Let's perform post-selection. This is a step in which we actually throw out some of our data. I'll explain why we'll want to do that. In a post-selection experiment, we'll again send some initial state into our experimental device. We'll operate on it with our transformation U. This parameter theta will be imprinted on the states, and then we'll perform our post-selection. We'll perform some intermediate measurements of an observable F. F is, in this case, a projector, so it has 2 eigenvalues, 0 and 1. If we obtain the outcome 0, then we throw our system into the trash, we stop the trial, and start a new one. If we obtain the outcome 1, then our state is projected onto some desirable subspace, which I'll call F post-selected, and then we'll let the trial complete. So we'll perform our final measurements and get some outcome from which we can learn about theta. Why would we want to perform this post-selection step? For example, suppose that our system consists of a photon. We're going to have to measure it with a photodetector. Some photodetectors have dead times. After such a photodetector detects a photon, then we have to wait for it to reset itself before it can detect the next photon. That delay is a time cost that we might not want to incur. So we should measure only the photons worth measuring. The intermediate measurement can help us ensure that we're measuring only the photons worth measuring. If we're using post-selection in quantum metrology, then again, we can quantify the amount of information we can obtain from our final measurement about the parameter we want to learn about, theta. So we need to calculate the post-selected quantum Fischer information. When we perform our post-selection measurements, the post-selection has some probability of succeeding so that we get the desirable outcome 1, so that the trial continues and we'll perform our final measurement. This is the form of the probability that the post-selection succeeds. And once the post-selection happens, if it succeeds, then our system is in this state. So we have our earlier states, we project onto the desirable subspace of our Hilbert space, and we renormalize with the post-selection probability. This is a pure state that we can substitute into our formula for the quantum Fischer information of a pure state, whose form I said we don't really have to worry about. And we get this expression, which also has a form that we don't really need to worry about. I just want to show you that this calculation is possible. We'll find a more useful form for the quantum Fischer information. Post-selection can improve the quantum Fischer information. Here's a really, really simple example that shows how. Suppose that in our experiments, we take stars, red stars or blue stars, and send them through some device that rotates the blue stars through an angle theta. Then our final measurement is of how far the star has rotated from this alignment. Suppose that we send a blue star in, it will be rotated and we'll measure the rotation, so we'll get a whole lot of information about theta. But if we send in a red star, nothing will happen to it. So we'll get no information about theta. So on average, over all of these trials, we get an okay amount of information. We can perform, however, a post-selection, an intermediate measurement. We can measure whether our star is red or blue. If the star is red, we can throw away the trial and start again. If the star is blue, then we can continue with the final measurement. In this case, the post-selected quantum Fischer information, when we perform the final measurement only on blue stars, is greater than the quantum Fischer information in the absence of post-selection. Because if we don't perform post-selection, we perform all of these final measurements and we get information from only some of them. The post-selection could be done here, or it could be done here. Instead of performing this post-selection, we could just choose a better input state. We could just choose only to use the blue stars from the start. That invites us to ask, whenever there's commutation of this post-selection and this operation, then can our post-selection do no better than just a better choice of an input state? Also, what if the processes fail to commute with each other, as we might expect to encounter in quantum mechanics? These are questions that we addressed in this paper. First of all, suppose that there is commutation. So in particular, suppose that this generator of the transformation commutes with the post-selection projector. Then we can do no better using post-selection than we can do by just choosing a better input state. Here's a brief sketch of why this should be true. First, we generalize that Kirkwood Dirac quasi-probability. This is my favorite step because it depends so very crucially on, or it focuses so very much on the quasi-probability. So this step was actually taken in an earlier paper. Remember, this is how we define the quasi-probability. It has a trace with two projectors and a quantum state. In particular, again, it has two outer products. Why not allow for as many outer products as we please, as long as we make a good choice of how many outer products to put in there, motivated by the physics of the problem? If we allow for arbitrarily many outer products, then we're allowing for an extended Kirkwood Dirac quasi-probability, which is a generalization of this one that was defined years ago. In our metrology problem, it will turn out to be useful to use a Kirkwood Dirac quasi-probability that has 1, 2, 3 projectors. So this is an eigenstate of the observable A, this is an eigenstate of the post-selection projector F, and also this is an eigenstate of the generator A. I'm simplifying the notation. I'm writing as though the generator A has no degenerate eigenvalues, but if the observable has degeneracies, then we can include a set of degeneracy parameters into our notation. I just wanted to keep the notation simple. Also, the ordering of the arguments on the left-hand side might look funny to you. If you're interested in learning about why I use this particular ordering, then feel free to ask in the question and answer session, but that won't really concern us here. Next, we find that we can take this quantum Fischer information, so the average information we get about the parameter theta per average trial of our post-selected experiment, we can rewrite that in terms of the quasi-probability. Here's the quantum Fischer information we're interested in. We said earlier that we can write down some expression for it in the presence of post-selection. And I said, don't worry about the form of the expression. It doesn't matter how the algebra is done, but you can show that this expression equals this expression. And here are two instances of our beloved quasi-probability. Now, let's suppose that those two operators commute with each other, the generator of the rotation and the post-selection projector. Since they commute, they share an eigenbasis. Let's choose for all of the bases in our quasi-probability to be that shared eigenbasis. Then, according to the properties that we saw earlier, our quasi-probability reduces to an ordinary probability. Using the properties of probabilities, we can upper bound the quantum Fischer information we can get from our experiment. It turns out that the quantum Fischer information, so the average information we can learn about the parameter theta per average trial of our experiment, is no greater than the variance. This is the bound that we saw earlier in the absence of post-selection. We conclude that if we're using post-selection in the presence of commutation of the two observables, A and F, that commutation stops the post-selection from doing it any better than we could do in the absence of post-selection if we just chose a better input state. What if the operators A and F don't commute with each other? Well, we know that in some cases, or we can show that in some cases, if we don't perform post-selection, then we get this amount of quantum Fischer information. We can choose our best possible input state, but that best possible quantum Fischer information in the absence of post-selection can be exceeded sometimes in the presence of post-selection. If this happens, if post-selection gives us a benefit, then it's because our quasi-probability distribution contains negative values, which means that our two operators don't commute with each other. This non-commutation is a key feature of quantum theory. So non-commutation seems to provide a non-classical advantage in metrology when we're using post-selection to try to learn about the value of a parameter theta. And my favorite part of all of this is it was this Kirkwood Dirac quasi-probability that showed that post-selection can give us a non-classical advantage helped by non-commutation, which is one of the reasons why the Kirkwood Dirac quasi-probability is my all-time favorite quasi-probability. You might have an objection. We perform a post-selection measurement, and we perform the final measurement, we continue the trial, only if the post-selection succeeds. It yields the desirable outcome. This probability that the post-selection succeeds might be low. So waiting for a successful post-selection might take a long time. So it seems that we don't really necessarily obtain an advantage from using post-selection. However, every operation in an experiment has a cost. It might be a monetary cost. It might be a time cost. It might be the cost of a graduate student. In some cases, the final measurement might cost the most. As we said, for example, photodetectors have saturation times. They have to reset after absorbing photons before they can detect the next photon. So the quantity that really matters is not just the amount of information we get out about a parameter per trial, but the information we get per unit cost, or the information we obtain from n trials over the cost of n trials. The information that we obtain is proportional to the number of trials. It depends on the probability that our post-selection succeeds, so we perform the final measurement and get some information. And also depends on the quantum Fischer information, the average amount of information we obtain about the parameter per trial. The cost of n trials also is proportional to the number of trials, as well as the cost of one trial. The cost of one trial includes the cost of preparation, the cost of the post-selection, and the cost of the final measurement if the post-selection succeeds. Suppose, well, in some cases, the cost of the final measurement might exceed all the other costs, so that we can approximate the denominator with just this one term. Then our information per unit cost is approximately this ratio. We can cancel some factors from the numerator and the denominator, and this result doesn't depend on the post-selection probability. So post-selection can boost the information cost rate regardless of the probability of post-selection. So this theory is being used in an experiment, photonic experiments in the lab of Ephraim Steinberg at the University of Toronto. Here's a very, very, very brief sketch of what happens. Our system that we input into the experiment is a photon, and we initialize it so that it's horizontally polarized. I'll label horizontal polarization with this 0 ket. The transformation acts in this way. So the results of the transformation is a superposition state. The state has a term with horizontal polarization and a term with vertical polarization. Our post-selection is slightly different than the post-selection I talked about earlier. It acts as this operator. Very loosely speaking, what happens is if the state is in the 0 state, horizontally polarized, then with very small probability, the system is allowed to go through and the experiment is allowed to continue. Also, if the system is in the 1 state, if it's vertically polarized, then definitely the system is allowed to go through and the final measurement happens. That final measurement is a measurement of whether the polarization is horizontal or vertical. So stay tuned. The paper about this will hopefully be out in the not too distant future. I've now talked about a number of properties of the Kirkwood Dirac quasi-probability and about how this quasi-probability can be used in, for example, metrology. So that information might bring up some questions. So here are some quick questions and answers in case you've been wondering. We said that if post-selection gives us an advantage over all non-post-selected experiments, then it's because the Kirkwood Dirac quasi-probability has some negative values. Is the converse true? If the Kirkwood Dirac quasi-probability has negative values, then can we necessarily use our state in order to obtain an advantage in post-selected metrology? The answer is no, but there is some measure of the negativity of the distribution that, at least in one case, is proportional to the amount of advantage we get from post-selection. Also, we said that if the quasi-probability distribution has some non-classical values, negative or non-real values, it's because operators don't commute. Again, is the converse true? If the operators fail to commute, then does the quasi-probability distribution necessarily have non-classical values? Again, the answer is no. However, you can ask, suppose that we have some system, we can characterize it with an extended Kirkwood Dirac quasi-probability. How much non-classicality is it possible to stuff into that distribution? How negative can it go? How non-real can it be? You can find a bound in this paper. So I've talked about one example application of this. I hope you're now convinced that it's wonderful quasi-probability in the context of metrology. There have been more applications of this quasi-probability in metrology. And what's more, as I mentioned before, the Kirkwood Dirac quasi-probability has been enjoying a renaissance across quantum physics. Many different applications have been discovered recently. I mentioned that this quasi-probability is relevant to how, if you measure a quantum system, it can be disturbed. The way that I came to this quasi-probability was through quantum chaos and quantum thermodynamics. Quantum state tomography, I mentioned, is how you can measure a quantum system to figure out which state you have in front of you. If you received the state from a friend or you prepared the state via a process that's not 100% reliable. I also just mentioned that this quasi-probability has applications in quantum thermodynamics, and it's been shown to be useful in the foundations of quantum theory. So if you ever come across a situation that might involve non-commutation in which a phenomenon looks truly non-classical, then you might find a physically relevant quantity like the quantum Fischer information that might decompose in terms of some generalized Kirkwood Dirac quasi-probability. Then you can assume that everything commutes with everything else, in which case the quasi-probability becomes a true classical probability. Then you might be able to bound the quantity the way that we bound the quantum Fischer information. Then remove your assumption, suppose that operators can commute, and you might find that you can violate the bound. Then you would find a physically relevant phenomenon that's sourced by non-commutation in a quantifiable way. So some possible applications include quantum computation and quantum error correction, where non-commutation is known to be useful. In summary, we talked about quasi-probabilities as representations of quantum systems analogous to phase-based distributions of classical statistical mechanical systems. I introduced my favorite quasi-probability, the Kirkwood Dirac quasi-probability. We saw how it's defined and that it has useful mathematical properties. We saw how it can be used in metrology to show that the non-commutation of operators sources an advantage if we use an extra step post-selection to learn the value of a parameter. Then we saw that the Kirkwood Dirac quasi-probability has actually been shown recently to be quite useful across quantum physics, and there should be more to be done with it. So thanks for your time.
Thank you very much, Doctor. I think Roman may have some comments.
Yes, I just want to say thank you so much for coming. I think everyone has greatly enjoyed this talk, and thank you so much for coming.
Thank you so much again for the invitation, and I'm so sorry again about the time mix-up. This is something that can only happen in the pandemic era.
It's okay.
Don't worry at all. I would like to open this space for some questions. If anyone in the meeting have some, they can send them directly to me and I can translate them. Franklin, I see that you have a question. Maybe you could write it to me if you wish, either in Spanish or in English. Maybe he's writing it, but I will ask you, first of all, do you see this generalization of the function, of the quasi-probability function, to be starting to be commonplace in many quantum measurement experiments and protocols?
It has definitely been measured quite a bit. So there are a number of experiments that have involved the measurement of this. And one example is the experiment in Toronto that I mentioned with photonics. So it's definitely not just a theorist's dream. It has been happening.
Thank you. I don't know, Franklin did not send me anything. Did he send it to you, David, or maybe Fernando?
Yes, I have one.
Go ahead.
From Dorian Lopez. He said, thank you for the excellent talk. Let's say that we have an optical interferometer to measure a sample's property, for example, the thickness, to use the quantum Fischer information to know the minimum thickness that we can measure. Do I need to use photons to apply the QFI? In other words, does the QFI require quantum states, or can we also apply it to classical systems using classical light?
We can apply it to classical systems.
I see.
So slightly larger explanation is the ordinary Fischer information is defined for experiments that can be classical or quantum. if you take the Fischer information and maximize it over all possible measurements, then that's what we call the quantum Fischer information.
There's also another question from Gloria. Wait a moment. She says if you could explain a little bit about how is the process of post-selection to final measurement, like what do you do in a real experiment?
Sure. Let me stop sharing my screen briefly so that I can go back to the right slide. Here's the photonic example. In most of my talk, I was talking about a post-selection that involved a projector. This post-selection isn't just a projector, but it's more useful to think about in this setup, and it's, in a sense that I won't get into at the moment, equivalent to a projector. But we have our photon that has ended up in this superposition state. Now, so we said that our parameter theta has some value that we don't quite know, but we have some guess as to what theta is, and the actual value isn't too far off. And we said that the expected value we would call 0. We set our number line that way. So theta is close to 0. We can do a Taylor approximation of this cosine term and a Taylor approximation of this sine term. So this cosine is approximately 1. So it nearly doesn't depend on theta at all. In contrast, this coefficient is, of course, this is 1/2. I'm ignoring the constant multiple. So this is about 1/2. It doesn't depend on theta. And this sine is approximately theta over 2. So this coefficient is linearly proportional to theta. So it's this term that carries the information about theta. But so we don't care very much about this term, but we don't want to get rid of it completely. Because suppose that we only performed a projector onto this one state, then after this projection, our quantum state would be simply 1. And that quantum state contains no information about theta. So we would like to keep a little bit of this state, this 0, in our quantum state, so that this theta continues to be multiplying the one state. So we act during our post-selection with this operator. We can think of it as letting through all of the light that's vertically polarized and letting through a very small amount of the light that's horizontally polarized. So that's how the post-selection looks in this experiment that's being done.
Great. I have another question from Franklin. He's asking, how is von Neumann entropy related to all of this? Is this function useful in this context? The context of the quantum Fischer information function and the surprisability, etc.
Yes, let me go back to another slide. This was the slide in which we introduced the Fischer information. We said that it's built from this surprisal. So suppose that we take the surprisal, and instead of taking the derivative and then squaring and then taking an average to get the Fischer information, instead we just take the surprisal and average it over the probabilities P sub b of theta. Then we get the Shannon entropy, which is the classical version of the von Neumann entropy. And suppose that you have a quantum state rho. The von Neumann entropy is defined in terms of the quantum states. So it's the negative of the trace of rho log rho. We can rewrite the von Neumann entropy as a Shannon entropy. The quantum state has as its eigenvalues a set of probabilities that form a probability distribution. The Shannon entropy of that probability distribution is the von Neumann entropy of the quantum state. So all of these concepts are interrelated.
Okay, I'm gonna send a last question from Ricardo Ancheta. Is it possible to boost the quantum Fischer information by post-selection measurements in quantum thermometry? For example, I do know that for thermal states, this is related to the heat capacity.
Could you repeat the initial question? I didn't quite hear it.
Yes. Is it possible to boost the quantum Fischer information by post-selection measurements in quantum thermometry?
Oh, interesting. It could be possible. Let's see. Quantum thermometry is a field in which we certainly want to perform measurements to learn the value of something, in this case, the temperature. And so the quantum Fischer information is relevant there. I haven't thought about how you might use post-selection there. It might depend on what sort of setup you have. You might have a setup in which post-selection is natural, as in this photonic example. And in that case, you might be able to use post-selection to your advantage. So that's an interesting possible application.
Great. Thank you so much for coming, Dr. Junger. I think we can finalize this session. So thank you very much, everyone, for coming.
Thank you for having me. It's been a pleasure.
Thank you.
Thank you very much.